we are dealing with the problem of aeronautic optimal shape design. So in aeronautic optimal shape design, we are dealing with important, of course, topic for guaranteeing global transportation of persons and goods, and on the other hand, highly technological, in which not only efficiency, but also safety is very important for all of us, right? And as we said, this is a complex geometrical problem because after all, the object we have to optimize is not just 1 or 2 or 3 parameters, right? Is a complicated, say, a 3-dimensional domain, right? Which is the cavity of the airplane within the space R3. So you see something that is interesting is that, you know, it's obvious in some sense, but it immediately shows one of the ingredients of the complexity of optimal design problems is that, of course, we are considering shapes, right, which are open bounded domains of R3. These are the shapes under consideration. Of course, the dimension of R3 is equal to 3. But if we consider, you know, the space S, the space of shapes, what is the dimension of that space? Could you please tell me what is the dimension of the space of shapes in 3 space dimensions? Does anyone have any hint about this? Some comments, I think. Infinity, precisely. This is something very important, right? So we are living in R3. The shapes we are considering are in R3. But the space of shapes is itself infinite dimensional, right? And you can see that very easily when you are looking to, you know, spheres, right? If you look only to the spheres, assume we were just designing balloons, spheres. What will be the dimension of the space of the spheres? If we just consider spheres, the dimension will be rather limited, right? Because basically it will be 3 dimensions for the center of gravity of the sphere, and 1 more dimension for the radius of the sphere. So it will be dimension 4, right? But of course, I mean, you can go to more and more complicated polygons and polyhedra, right? Which will be needed in order to be able to approximate any shape. And you see how, as soon as you are increasing the number of sides, right, in this polygonal or this polyhedron, the dimension is growing endless, right? So even if we are considering a simple geometrical problem in R3, the mathematical problem of optimizing the shape, right, is formulated in a space of infinite dimensions, right? Where you encounter all the difficulties related in particular to the fact that bounded sequences do not necessarily converge, right? They will only weakly converge in the case of reflexive Banach spaces, and this will generate, of course, many technical difficulties. So this on one hand. The classical problems in industry in which you try to optimize shapes in order to generate a kind of optimal process, these problems are infinite dimensional. Now, they are infinite dimensional problems in the sense that you are considering parameters, the variables to be optimized, live in an infinite dimensional domain. On the other hand, the criterion you have to optimize in order to design the airplane are multifold. They are multiple, right? So in particular, in order to analyze the stability of flight, you need to consider the drag, the thrust, the lift, and the gravity, right? So the functional you will have to minimize, as you do in multi-criteria optimization problem, right? So if you do multi-criteria optimization, the way we do it is we say, well, the functional J that I'm going to minimize will be a weighted combination of several functionals, right? So one functional will take into account, you know, the lift properties of the airplane, the other one, the drag, the other one, the thrust. There could be criteria also related to the weight of the aircraft. There could be criteria about, you know, the volume, the height, the comfort of passengers inside, you know, the oil consumption. There are many, many different criteria you need to optimize, right? So, and then, you know, the question will be how many of these criteria you put into the functional you are minimizing. That's first. And the second one is how do you weight the different coefficients, right? Because of course, depending on how do you choose these weights, alpha I, you are giving more relevance than to one functional than to the other. Okay, so you can see that when you are simply considering, you know, two parabolas, right? So you take two parabolas, one, you know, with a minimum at -1, and the other one with minimum at 1, right? So you say, well, this is the parabola x plus 1 squared and the parabola x minus 1 squared. In case, you know, this is a very simple representation of what happens in general optimization problems. You have two criteria to be optimized, right? One, according to one, if we will minimize simply the first parabola, the optimum will be -1, right? So you are with friends and you have to decide whether you go to the restaurant or you go to the park. So according to the first criterion, you go to the restaurant. According to the second criterion, it's very nice outside and you want to go outside. You go to one. So to which place you finally go, right? So then the answer, of course, will depend on how, you know, do you choose in your functional to be minimized the weights alpha plus and alpha minus. So please check, right, that depending on how do you choose these parameters, right, you can in particular get to any intermediate point, right? The intermediate point of the minimizer of this new functional will be depending on the mutual ratio between alpha plus and alpha minus. And this will be so simply, this will be so simply because depending on how do you choose alpha plus and alpha minus, you will be given more relevance to criterion 1 or criterion 2, and therefore the minimizer will either be rather closer to -1 or closer to +1. Okay, so this is how, you know, the main challenges on, you know, in particular aeronautic industry, some of the main challenges of optimal shape design in aeronautic industry from a simplified mathematical perspective are viewed. So now when you see this, you say, well, but this looks to be a purely geometric problem. It's purely static. Where does dynamics appear, right? Where does control theory appear? Well, it appears because the models, right? The models for continuum mechanics are given by the Euler and Navier-Stokes equations. So in particular, whenever you have to compute J omega, right, you need to solve, right, solve Euler or Navier-Stokes equations in the space R3 minus omega, right? Why R3 minus omega? Well, because the aircraft is occupying a given shape, right? And the air, you know, is flowing around. And the fluid, right? The fluid, which is the air, is precisely occupying the stereo space that the cavity omega leaves. So you see that in order to compute J omega, you have to solve the equations of fluid dynamics. That will be Navier-Stokes, Euler, or even more complete and sophisticated and, you know, models. Okay, and then you say, well, but then how did aeronautical engineers succeed, right? Because when we look to the, you know, how complex the fluid flow can be, the solutions are extremely complex. They can be very turbulent. They can be chaotic. They can be, definitely, it's not a nice Gaussian solution that arises by solving a simple linear heat equation out of a Dirac delta. So, you know, the analytical solutions in that case are not accessible. And computationally, certainly, this is a very demanding problem. Actually, as I said the other day, out of the 7 millennium problems that were advertised back in 21 years ago, with the turn of the century, only one of them was solved by the Russian Perelman. The 6 others are open, and one of them is related to the Navier-Stokes equation, in the sense that the Cauchy problem, right? So solving the Cauchy problem, in this context is open. Okay, so here the Cauchy problem is open. Right? So in 2 space dimensions, there was a seminal paper by Jean Leray in Paris in the 30s, so 80 years ago, essentially, where he followed the ideas of Cauchy, saying, you know, I should consider Navier-Stokes equation in the full space, take an initial datum, for instance, in L2 of R2, and then try to prove that there is a unique solution which is continuous with values in L2, right? Has a gradient in L2 space-time and so on. And he was able to address this problem completely in 2 space dimensions, right? Nowadays, this is a not so complicated theorem. If we know a little bit of evolution equations, semi-group theory, we can formulate Navier-Stokes equation as a fixed point problem in the variation of constant formula, right? The integral representation of the PDE out of the linear semigroup. And we can show that there is existence and uniqueness of solutions. But this is open in 3D. Okay, it was solved in 2D by Jean Leray in the 30s. So now how it may happen that even if we don't know how to solve the Navier-Stokes equations, we are able to simulate such flows, right? And even if we don't have a complete clear picture, we can address this challenging problem of fluid dynamics, given that necessarily when we try to compute the cost functional to be minimized, one has to go through the resolution of Navier-Stokes out of the, you know, cavity omega in R3 of minus omega. So this is, of course, thanks to the computer and computer sciences and numerical mathematics and computational mathematics, right? So nowadays, thanks to modern computers, which are extraordinarily more powerful than the traditional ones, like for instance, those in the Second World War, right? We can, even though we don't have a very good analytical understanding of the Navier-Stokes equation, we can build numerical schemes that are able to run quite reliable simulations on the performance of a given cavity. Okay? And in this way, right? So in this way, we can assess how good, a design omega is in terms of a precise and accurate approximation of j omega. Okay? And then once you know what the value of j omega is, right, you can decide whether the design you have is okay, is good enough, or whether, right, or whether you need to, right, improve the design to get a new one, right? This is the key. Okay, computational mathematics are the key. And then it's also very, and this is one of the strengths of mathematics, right? When you talk to people that are not mathematicians and then they tell you, well, but what do you do as a mathematician? You just solve tricky problems applying pre-cooked formulas. No, this is not what we do. I mean, of course, there are some basic formulas after, at some given time you will remember, right? So the Green's formula for integration by parts, right? And there are classical recipes that you will memorize, like the convergence of the dominated convergence theorem, or you will recall basic algorithms like gradient descent for optimization problems, or the basic principle of Lagrange multipliers. Of course, as a trained mathematician, as a professional of mathematics, you will memorize all this, and this will become more or less automatic on your daily applied mathematical work. But we are, above everything else, what we are doing is developing methodologies that are able to address more and more challenging problems. And the beauty of, the control theory and the optimal design theory in continuum mechanics is that, for instance, all the methods that have been developed in order to deal with aeronautics can then be also used in the context of the cardiovascular system. Why? Because the computational tools that are used in order to compute complex flows around an airfoil can also be developed in order to, and implemented in order to compute, blood flow on the human cardiovascular system along arteries, right? And thanks to this, then you can, for instance, contribute to improve the design of the, for instance, stents, the artificial devices that are often used in order to improve the cardiovascular health of people that are undergoing some cardio deficiency or sickness. Okay, so let me now show you how control theory can play a role. So this video was given to me by my colleague and friend Jean-Michel Coron from Paris, right? And let's see what happens. So this is a water tank, right? So I mean, if you take your aquarium, so if you have an aquarium at home, you certainly know how difficult it is to take the aquarium, right, from the living room to the kitchen while it is full of water and the fishes are inside, right? So you wanted your fishes to be comfortable, so you have kept the water in, but then you decided to move the aquarium from the kitchen to the living room because it's nicer to sit, really where you spend most of the time and you relax. Okay, so now you have all experienced how difficult it is to bring this aquarium from one place to another without, you know, putting water everywhere, right? And also then risking that eventually if the aquarium is empty, the fishes will die. So in this simulation, what we see is, you know, the same aquarium, two eyes, one to the left and one to the right, you know. There is an initial excitation of water. This will generate waves. And then, of course, if you let the system evolve, after some time, these waves will dissipate and you will reach equilibrium. What is equilibrium in this case? Equilibrium is this configuration drawn here, right? In which, you know, the level of water, the height, is constant everywhere. This is a nice equilibrium. You see here some gates, right? So this is due to the fact that this simulation is intended to be applied to, you know, to the navigation along rivers, right? Where very often, as you know, you have to regulate height, right, of water by employing these gates that will open and close, right, in order to equilibrate the level of water, and in this way be able to navigate on a topography which is not necessarily flat. Of course, if you were living in flat land, right, in a completely flat universe, then you could navigate without any concern, but you have to adapt to a topography in which there can be several meters of, you know, of gap, right, on the height, and in order to do that, you have to maneuver in order to be able to equilibrate the level of water, letting the ships go through. Okay, so then, as I said, there is an initial perturbation, and in the left side of the video, you will see how long it will take to these oscillations to dissipate spontaneously, right? And on the right, you will see how by controlling, by acting, you will not even perceive it nearly, right? But if you act, you know, on these walls by introducing some micro vibrations, you will be able to stabilize these initial waves much faster, okay? And this is the simulation. So you see waves to the left and to the right, right? But you see how fast on the right, right? You see how fast on the right you go to equilibrium and how long it takes on the left, which is, you know, spontaneously evolving to get to the same configuration. So here, right, in this problem, what we have done is to show how active control can speed up the stabilization process of natural phenomena. In this case, is the phenomenon under consideration is the dissipation of waves, right? So maybe we can see the video again. So you see on the back how rapidly the control mechanism is able to bring, right, the configuration to a nice equilibrium, and how, you know, it takes a few more seconds in order to do it in the first case, the one on the front, where you are not acting on the system, but just waiting that waves stabilize under the effect of gravity. Okay? So you see again, I have bring this simulation here because this is again a simulation which has to do with control, and in this case, control of water fluid mechanics again. Okay, but now you see we have discussed the calculus of variation, controllability problems, optimal design. So all these fields are, you know, interlaced. They have common borders and common, you know, interfaces. actually, it is very much to the mathematician, to the scientist that is addressing these problems to decide how do you model it and what are the mathematical techniques you apply to address it, right? But eventually, as we have discussed in the context of Navi's talks, independent on how well you master the analytical aspects and how rigorous the mathematical theory is, eventually, of course, you will always have to deal, to bring these problems to the computer, right? And this is why optimization theory is so relevant, right? Okay, so the classical problems in logistics, for instance, where, the typical problem is, the typical problems of linear programming, right? So you certainly know this, right? So, a company, is dealing with several items in different, say, storage locations. And then there are a number, you have like M items in M locations. Then you have N clients. Clients are asking you, right, are ordering different goods in different volumes with different combinations, right? And you are the company, AliExpress, or you could be Amazon, or you could be any online selling company, that now you are getting, purchases, clients buying different goods from different places, right? Bicycles from Changchun, cars from Chengdu, motorcycles from Fudan, books from Shanghai. And you have to organize this process of, transporting optimally all these goods to these cities. Of course, you could do it one by one, right? Whenever someone you are working, I don't know, in the premises of the company in Beijing, whenever someone is ordering by telephone or online, probably more online than on the telephone nowadays, someone is ordering one good, you put this good in a motorcycle. Will this be optimal? Well, probably not. It will be simply impossible. There are too many purchases nowadays ongoing. Every second, people are buying goods. So it will be impossible to just use many motorcycles and motorcycles drivers and bring these goods there, right? On the other hand, it will take too long. This will imply many people, a lot of risk, and a lot of expenses. Eventually, the selling will become expensive because you will be paying a lot for the salary of the drivers, and your company will not be competitive. So you have to optimize, right? So you have to, this is a purely combinatorial problem. You have goods in different locations, you have buyers, and the only thing you have to decide is how, you put, combinations of these goods into containers, right? And how these containers are driven by, are taken by airplanes or trains. So to move, to the destination collectively, so that then the distribution problem is purely local. And then, yes, it can be done by the post officer or by the motorcycle driver. So this problem that looks quite elementary, after all, is about finding the corners of a polyhedron in a Euclidean space, or if you want to, is to simply minimize a continuous, even linear, right, or quadratic functional in a bounded and closed set of an Euclidean space, which is defined by hyperplanes depending on the constraints, right? How long do you have to deliver? How many, different containers do you have in order to organize your distribution and the delivery? So there are several constraints, right? How much money you can spend on the process. So these are all linear constraints, unilateral constraints. So this problem that is so simple, apparently, because from a mathematical perspective, this is something we learn in the first year calculus in the bachelor program, right? The professors say any continuous function in a compact set of Euclidean space have a maximum and a minimum. So then it's fine. You can say there is a solution for this problem. So you are running a complicated company on internet selling, and you wonder what is the optimal programming of the distributions of goods. Then if you have a mathematician in the company, you will ask the mathematician, and the mathematician will tell you, boss, I mean, don't worry, there is an optimal solution. But this is not enough. You need to compute it, right? And this is what linear programming does. It not only gives you an answer to the problem, we know there is a solution. The question is how rapidly I can compute it. Because depending on how fast I am on computing, you know, I can refresh my simulations, right? And adapt myself on a dynamical manner, on a dynamic feedback form to the simply, you know, always endless changing market, demands and offer, prices, availability, weather conditions, to all kinds of circumstances. So this is why, even though if you start from a very sophisticated problem, which apparently has nothing to do with these very simple questions in logistics, simple apparently, but extremely complex computationally and extremely relevant, right? This is why, you know, classical methods like the interior penalty method for, you know, linear programming is one of the seminal, say, computational methods. One of the methods like finite elements for solving partial differential equations, or the fast Fourier transform when you are dealing with frequency analysis. So this is one of the seminal contributions and one of the computational, say, tools that is most often utilized, right? Is because not only some problems fit naturally in this context, but many others, like those I mentioned before, like optimizing the shape of an aircraft, once you discretize the problem, something that you necessarily have to do, right? When addressing, you know, the actual computation of the simulation, once you discretize the problem, you get into similar issues. And this is why optimization theory is so broad. I mean, you will see subfields like convex programming, linear programming, semi-different programming, stochastic programming, robust programming, right? You certainly know. This is one of the most, say, relevant fields in applied mathematics. Nowadays, we are lucky because so much, you know, theory and methodology has been developed on this, that for a number of years now, there are even, you know, teams of applied mathematicians that have developed software, right? You can, for instance, find yourself this software online. You can download it for free. You can also use it online. This is IP-opt, IP for interior penalty and opt for optimization. This software was developed in Carnegie Mellon in Pittsburgh in the United States by teams originated in computational chemistry, right? So it's about, you know, optimizing very, very, very long chemical processes in which, you know, several reactions are in chain, and therefore you end up dealing with systems of differential equations in cascade, one after another, in which you have to optimize parameters in order to, for instance, refine oil, right? And then eventually, again, as usual, the problem intellectually is not so difficult to understand, but in practice, it is very, 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 very hard to solve, right? Because, I mean, analytical methods, you will never be able to find a closed form of the solution. And even though we know that the solution has to exist, in particular, once we bring this problem to the context of numerical analysis, where the question is about minimizing a continuous function on a compact set of the Euclidean space, it is actually very, very, very hard to solve, okay? And this is something that we have explained and discussed in particular in our blog. I can maybe show you in internet the blog that we have developed in a European Research Council project we are running. And okay, so this is it. Okay, so I share my screen now from the computer. Okay, you see this DICON toolbox, right? So this is a, a toolbox developed in the context of a project funded by the European Research Council. The name of the project is DICON, Dynamic Control. You will see also, right, in here, you see the toolbox, right? So where you will find a manual of the possible use. You can download it. It is basically, it combines basically MATLAB, IPOpt, and Cassadi. So, we didn't do anything completely from scratch. Our idea was to do something as simple as possible, right? So that you can go a little bit beyond, the classical control toolbox of MATLAB and develop something that is more adapted to deal with problems of this form, where you are, for instance, controlling a dynamical system, depending on, for instance, some parameters, right? The control lives in a set with a given number of constraints. And then the question is, how do you, minimize a cost given this multi-criteria optimization problem, in which you are not only considering the dynamical system for a given value of the parameter mu, but for parameters on a given range, right? And this becomes then a multi-criteria optimization problem. Of course, the problem is always apparently simple, but as I said before, when you increase, the complexity of the dynamics, you increase the dimension of the space of parameter, you face very rapidly the course of dimensionality, and therefore it is very necessary to have tools which are extremely efficient, right? So you can download this toolbox for free, right? You can install it, you can play with it, you can solve the problems you have in your own laboratory or project using it. And of course, if you have any questions, you can ask to us. As I said, it is combining tools that are already existing. One of them is automatic differentiation. I will come back to this later. The other one is IPOpt that I just mentioned. And of course, concepts like Runge-Kutta methods for discretizing differential equations, Pontryagin maximum principle for characterizing the optimal control, right? And the MATLAB PD toolbox in order to discretize PDs. Together with the toolbox in this web page, you will also find examples of problems that have been solved, and that could inspire you to see what can you do and how can you do it depending on the application you have in mind. So we see here, for instance, an application to the fractional heat equation. This is about collective behavior and the analogy with diffusion processes. This is a classical problem of stabilizing a mechanical system, a pendulum. This is simultaneous control. It's about dealing, simultaneously with many different realizations of a process. This is more about the synchronization on a dynamical system, right? So Kuramoto system for nonlinear dynamics and so on, right? And together with this software, right? You will find also, you know, in our webpage, you will find also the blog, right? In which you will find posts, right? That explain, you know, the different applications, right? And it's kind of a short summary and synthesis of, right, developing, right, the theory. Normally you reflect on a mathematical article, right? And then the computations that normally, you know, are marginal often when you publish a mathematical article. So here we develop and we present in a more, say, friendly and dissemination manner, right? Some of the applications we have developed. So this is, for instance, the classical paradigm of co-learning, right, for finite dimensional problems. And you will see how it has been implemented. And then in the end, you have a video in which you explain and you can visualize how, you know, a person that is living in this cavity and, you know, is not able to see where the door is because everything is hidden. Finally, this person can develop a machine learning strategy in order to, you know, to get out of the cavity quite fast, right? So this is as you know, this is a combination of, say, dynamic programming, optimization theory, and also a little bit of stochastics and Monte Carlo in order to guarantee that you don't spend, you know, too much time exploring here on the walls where the door, you know, is not there, but rather to try to orient yourself rapidly to the most, say, beneficial wall, which is this one, and eventually find down the exit from this labyrinth, right? Okay, there are several simulations presented. Of course, you can make the problem more complex if you put obstacles inside, which do not allow you to, you know, to cross, right? And you see, for instance, in this simulation here to the right, how this particle, which is lost in this cavity, and furthermore encounters all these walls, which are given by these dark blue rectangles, right, obstacles, eventually is able to find a corridor to pass by and get rapidly to the door using this co-learning paradigm, right? So, but you can see many other posts. I mean, this will be something completely different about you know, network dynamics and many others, right? That you can you know, visualize with time. And I think this could be something very, very helpful for you to get inspired to run your own projects. Very good. So this is about the relevance. Sorry. Yeah. So this is about the relevance of scientific computing in combination with control theory, right? So my recommendation to all young fellows is that, well, I know things are getting more and more difficult because nowadays you don't only need to know mathematics. Of course, everyone thinks you should be you know, master the main tools of mathematics, but you need also to, you know, to be able to manipulate computers and be efficient on scientific programming and scientific computing, right? And not only this, nowadays you have to be ready not only to face classical applications like aeronautics, in which, you know, the equations of continuum mechanics are given, but also to be able to address these new challenging problems coming from machine learning and data science. Okay, so as I said, the perspectives of this field are huge. So nowadays we are, you know, for mathematicians, this is the golden age in which young people getting a diploma, I mean, they often, you know, don't wait even 1 week in order to get the first job offers. mathematicians are extremely evaluated nowadays in the job market, and in particular, those without training in the topics we are covering here, right? So topics that belong to the core areas of applied mathematics, but on which it is not sufficient to know something about, the stability of dynamical systems, or to be able to solve very precisely partial differential equations of a given specific type, or just to know some, very specialized techniques in optimization theory. The challenge is that nowadays you have to know a little bit everything of each of these areas, and you have to be able to combine them intelligently when you are really facing modern applications that, as we will see now, are getting more and more complicated. So you will not only be dealing with the classical problems of, say, applied mathematics, right, as those I presented before, right, but like, mechanics, right, mechanics and electricity and chemistry and biology and economics. But oftentimes you will be dealing with problems of a very high level of complexity, in particular in which network theory will be extremely important, right? So, and then as I tell you about networks, of course, you can think on networks of different levels of complexity, right? So this is a star network. So everyone understands what a star network is. There is a center, and then there are radii emanating out of this center. Some are longer, some are, shorter, but there is not much you can do on this, right? So, I mean, if you are here, the hub, right, like the big airport in Beijing, and you have to deliver airplanes to the different towns in China, well, I mean, depending on how far they are, and depending on how, big the destination is, you will plan, more frequent flights with bigger, aircrafts and so on, right? And if for some reason you have to go from here to here, right, there is not much doubt in here, right? You have to first take an airplane to go to the hub, and then in the hub take a second airplane to go to your home, right? Of course, things are normally not that way. This is a much more realistic, network in which you have different hubs, different stars, but these stars are interconnected. So now when you are planning your trip, right, from this location to this one, then you will see that there are several combinations, right? Because you could go from here to here to here to there, or you could go from here to here to there. And this is actually something you see when you are buying an airplane ticket online. There are several criteria in order to discriminate one ticket and the other. Of course, for us, the most important is normally how expensive the ticket is, right? A second criterion you can see is how long the total travel will be, right? And then you will prefer a trip that is taking 10 hours so that you can do it during daytime. You leave 8 a.m. from home and you get there at 6 p.m. than a trip that is taking 16 hours, which means that you will spend overnight on the airplane. But then there is another criterion, is how many times you have to change, plane, right? The same when you are traveling on metro. Sometimes you prefer to take a longer metro, even if it takes more time. If the metro is direct, it's quite comfortable to sit. And then on the trip, during the trip, even if it takes 1 hour, you can read, you can do something, even, deal with your, your mathematics, or respond email, or, prepare an exam, right? Rather than trying to, shorten the trip by maybe 13 minutes. But to do this, you have to change, metro 3 or 4 times, right? So we know all this. So there are different levels of complexity on the networks. And nowadays, modern applications in social sciences, social networks, commerce, economics, finances, politics, international relations, multiculturalism, right? Energy, transport, everything is related with the theory of networks. So not only nowadays, all we have done in control theory, in optimization theory, in the calculus of variation is very useful, but not only we use it the way it is, but nowadays mathematicians are facing the challenge to move all this theory into a different level of complexity in order to face modern applications in a way that is feasible, right? Because otherwise, yes, you could always say, I apply for such a complex scenario the same methods I was using until now. Yeah, the problem will be that the computer will take so many hours to compute the solution that this will certainly not be viable, right? And as I said, nowadays we are more and more influenced by the need of combining continuous modeling with the modeling of discrete, right? Graph theory, networks, statistics play a more important role, right? Data mining, big data, data sciences, machine learning, statistical learning, and key areas. And we are also facing new challenges, as I mentioned before, due to the fact that we are, living in a increasingly populated and more complex world, where multiculturalism and intercultural communication plays an important role, and also we live longer. Which is leading to the emergence of also new form of neuro scientific questions that we need also to address, right? As you know, mathematics, you can specialize, and you have to specialize when you become a professional, but mathematics is unique. And in that sense, as you know, you can, for instance, check yourself once you are a professional mathematician and one of your papers is published, right? You can, in MathCNet, right? The database of mathematical articles that is run by the American Mathematical Society, and normally you have access to it through your university account. You can compute what your Erdos number is, right? So Erdos was a celebrated Jewish-Hungarian mathematician in the end of the 20th century. He was very prolific. He wrote many articles in number theory, combinatorics, graph theory, and he did it with so many people that nowadays, right, you can easily see how true the paradox of the small world applies when you are talking about, the mathematical community, right? So in that way, the MathCNet web page will give you your Erdos number. So what does it mean, Erdos number? It means that Erdos, who was working with so many people, maybe he had like 300 collaborators, or those collaborators that wrote an article at least and published an article with Professor Paul Erdos, they have Erdos number 1. But then those that collaborated with the collaborators of Paul Erdos have Erdos number 2, right? So for instance, I have Erdos number 2 because I never collaborated with Professor Erdos directly, but I have an article or maybe 2 articles written with a person who collaborated with him and who has Erdos number 1. Because of this, all my collaborators have at most Erdos number 3, because they collaborated with me that I have Erdos number 2. Of course, out of the collaborators I have, all of them have a maximum Erdos number of 3. Many of them will have also an Erdos number 2, because other than collaborating with me, they collaborated also with other people that have Erdos number 1, right? So, and this is a very interesting exercise, because this web page will tell you how close you are, how many generations far, generations in terms of layers of cooperation, scientific cooperation, you are from Erdos. And you will see also that sometimes the path to Erdos is not really the one you expected, but it occurs here, you know, like in these networks in which, you know, sometimes the path chosen is not really the most intuitive one. Okay. Now, as I said before, none of these applications will be possible if we were doing simply theoretical mathematics, right? So theoretical mathematics, theoretical understanding is the must. It's a must. And this is often what mathematicians will like the most, right? So getting a, you know, in face of a problem, right? So for instance, nowadays there are many applications in machine learning like reinforcement learning, federated learning, supervised learning. So what a mathematician likes the most is the possibility of formulating this problem in mathematical way, so that then you can develop your ideas, build methods, combine your own understanding from other fields like dynamic control theory, gradient methods, to come with a, say, interesting analytical solution. But nowadays, as I said, when you are really facing applications, you need also to go through scientific computing. You have to bring concrete answers, right? And this is this was taken from the web page of Professor Nick Trefethen in Oxford. This is a list of algorithms, right, that you know, were developed historically, and here we are only including you know, the some of the most say fundamental ones, right? So you see here that Gauss elimination is written in year 263. So when you see this, you see, oh, it seems it's wrong. No, but Gauss elimination before it was developed in Europe apparently was you know, already, you know, initiated by a Chinese ancient mathematician, you know, like 18 centuries back. And then you see the modern development of, you know, physics and mathematics, where you can encounter, you know, Newton's law, least square, Runge-Kutta, finite differences, splines, Monte Carlo, simplex algorithm, Steve ODEs, fast Fourier transform, spectral methods, multigrid, precondition matrix iteration, MATLAB, wavelets, and then finally here, automatic differentiation. So this list is, of course, not complete. This is just one list of some of the most fundamental, say, computational developments, and also the names of some of the contributors to these fields. Okay, so this really is to enhance the importance of combining nowadays methods from analysis with computational mathematics. So when Professor Kai Sang invited me to deliver this series of lectures, and we discussed about the context, we said, well, so you see nowadays, control theory, optimization theory is undergoing also an important metamorphosis, right? So why is that? Well, it's because, you know, the mathematics are the same, but the problems that are, you know, challenging the scientific community take often a different form, right? And this is what happens in particular in the context of machine learning. So in this you know, end of this first part of the lecture today, I wanted to motivate, you know, some of the contents we shall also develop in this course is, I mean, what is the link between, you know, these classical tools like control, optimization, calculus of variation? What is the link of all these fields with the modern applications in machine learning, right? And let me do it by a simple example. So how do, you know, classification problems arise, for instance, right? So, I mean, you can check yourself, you open your, your cell phone or your computer, and you can, you can check, I go to the photo folder, and then the telephone says, well, your photo folder is full. You have, I see here, 6,000 photos. If you have to look for one photo, and you have to check one by one these 6,000 photos, it can take a long time. So you better have them classified on your phone. You can classify them by locations, where the pictures were taken, by years, in which year the picture was taken. I mean, this could help you, because then I was, in Changchun back in 2019 in the summer, so I go to July, August 19 Changchun, and I will find the photo easily, right? Or more easily at least. So I will not need to search among 6,000 of them, but just about maybe among 100 of them, okay? And that's much faster. So you have to classify information. So another practical application is, of course, when you are managing, the recycling of urban residuals, right? Where, for instance, in Germany, there are, also in Spain now, right? So in most European countries, you have several containers. I suppose that this is more or less the same in every country with small variants, right? Where, the convention is, the convention can change from country to country, but the idea is that, plastic will go to one container, glass will go to another container, paper will go to another container, and then organic food will go to another container, okay? And this is something that at home, it's not so difficult to do. Whenever you have to put something on your, garbage, you just check and you say, this is a paper, right? So if this is paper, and then when I put it on the garbage, I will put it in the blue container. But if this is plastic, right? So I don't know whether this is an Apple Pencil. I don't know whether it's plastic. There is probably a battery on it or not, but probably. But if it was just plastic, I will put it in in the yellow container. But if I take a cup, a glass cup, then it will go to the green container and so on, right? Okay, so this is something that we all understand very nicely. We know that in some occasions, things are not so tricky. There are materials like this coupon I have here that when I touch, I say, well, it looks like paper indeed, but it seems like to be plastified, right? So maybe this is a composite material. Maybe it's in between yellow and blue. So I'm not sure where should I put this kind of card, which is partially paper, partially plastic, right? So I'm not sure. So maybe I can just allocate a probability, a higher probability to be plastic. So I put it here in the blue, but I'm only sure about 80% that I'm doing right? Because it seems there are elements that could also go to the yellow part. But the way this coupon is done by unhomogeneous, composite material, I cannot separate plastic and paper, right? So I cannot split it into two pieces to put 20% here or 80% here. I have just to choose one or the other. So I choose blue because it is more likely that there is more paper on it than plastic. Okay, so you see the problem can become also quite sophisticated. The question becomes much more challenging when you are not doing this at home, but you have to classify. You are running a plant, a big plant in a city where you are recycling automatically the residues that the city is generating. And then you want to build an engine, a machine, a robot that will do that automatically, right? So the robot will have to, whenever something new is coming, the robot will have to, on real time, the robot has to decide this bottle is plastic, goes to yellow, but then the next bottle is glass and it has to go to, to green, but the next box is more paper and then it has to go to blue and so on. So you need to automatize the process. And you remember, this problem that nowadays is considered a problem of classification or supervised learning. One of the basic paradigms in machine learning, we say, well, I mean, you can call it machine learning, but this is control theory, right? Because this is precisely the goal that, Aristophanes indicated 2,500 years back. He said, humans will need to make processes automatic so to be free, right? So you want your frigo to be operating automatically. You don't need to be concerned about whether the fridge in the kitchen is keeping the food cool. We know it's working. So because I know it's working and that electricity is coming to the room automatically, right? I have a good working atmosphere, right? I can talk to you and I can focus on delivering this class, talking to you directly, right? Otherwise, I will have to be, stopping every second because I will have to deal with the air conditioning, with the electricity, with the water, with the frigo, the washing machine, the dishwasher, every device at home will require my attention. The modem, right? Okay, good. So we need to make this process automatic. So now you see, we call it machine learning, but this is actually the goal of control theory. What is the difference? What is the difference in this problem? So this is a machine learning problem, right? So this is a machine learning problem, right? My claim is that, it is also controlled. The main difference in this case is that we don't know what the model is, right? We don't know what the model is. When I was considering, for instance, this problem of, the water tank regulation, in here I know, yes, of course, there are equations in fluid mechanics for such a problem, right? So we have Navier-Stokes for the three-dimensional fluids, and here there is, the shallow water, right? Equations, which are a simplification of Navier-Stokes equation that has been driven, right? Have been written, have been derived in order to deal with the propagation of water on canals where the depth is low, right? Of course, I mean, you cannot apply the shallow water equations when you are in the middle of the Pacific Ocean, where, the depth is thousands of meters, right? But when you are dealing with water on an artificial canal where the height is of a few meters, you can apply this simplification and basically ignore the third variable or even ignore the width and simply propagate waves along the longitudinal variable, making the system to become much simpler, right? And there are many equations like this that have been derived out of the complete Euler and Navier-Stokes equations, right? Like KdV, Korteweg-Debrye equation for the solitons, the shallow water equations of Saint-Venant, and many other models. Okay, good. But in those cases, we have models, we have PDEs, right? So if you write, if you write KdV equation where you have the typical ingredients are time derivative, third derivative with respect to x for the dispersion in a space, the classical nonlinearity of Burgers in order to, to generate, right? In order to generate nonlinear waves and so on. Good. But now when I come to machine learning, to supervised learning, so the first question I have to address is, okay, so we say that this is machine learning. My claim as a control theorist, and this is that this should be control as well. But then the main question that arises is what the model is. do you think I can apply the equations of mechanics to describe how, you know, waste according to different categories has to be placed on different containers? Can I apply the equations of fluid mechanics, like for water, for air, for blood? Can I apply the equations of elasticity? Can I apply the, you know, the equations of classical mechanics for, you know, for the orbits on the planetary solar system? So which equations can I apply here? Does anyone have an idea of what are the models in mechanics I could adopt in this setting? Any suggestion among the audience? What could I do? So maybe I can apply solid mechanics. I go to Math.CNET and I look to the math classification table and I say, well, I mean, there is continuum mechanics, there is solid mechanics. Oh, maybe this is solid mechanics. No, solid mechanics is not about this. Solid mechanics is about, indeed, you know, the deformation of solids, right? So elasticity, viscoelasticity, plasticity, but we'll not be dealing with these problems, right? There is no dynamics. So one of the main, say, differences between the classical applications of control theory and the modern applications in machine learning is that, you know, the dynamics is not given, right? So when I observe the planets and the moon and the sun and the rotations and the periodic, say, motion of, you know, meteorology, climate, atmospheric sciences, astronomy, astrophysics, and so on, the laws are somehow given. Well, at least this looks to us that way. You know, 400 years ago, it was not so clear. Before Newton, you know, discovered the laws of, you know, the gravitational forces and explained how planets and, you know, were attracted mutually according to the laws of universal gravitation. It was not so clear that there was a law describing how the universe was evolving. Before people were able to write the equations of meteorology out of, say, fluid mechanics, and then develop, you know, efficient computational tools in order to anticipate weather. So now you can check on real time, right? I go to my telephone and then I check and I see the weather today here in Bilbao, where I am now in Basque Country in Spain, is 19 degrees. But tomorrow is going to be 22. And on Monday, it will be 27 and sunny. So I can now anticipate the weather. This is clear now, but it was not so efficient 100 years ago, of course, or not even 40 years ago. So we wonder whether at this point we are in the presence of a process for which there is no model, or maybe the question is that our understanding is not good enough so to have a clear idea of what the model should be. In any case, nowadays we can say there is no model. As far as I know, there is no ordinary differential can, you know, guarantee that the yellow should go here and the glass should go here. There is no such a model. So the machine learning, to a large extent, is about control without model. Oh, and you wonder then how I do it. because I open the books in control theory, and the books in control theory, as we have presented the previous days, will say, okay, you give me a system like x prime of t equal a matrix A times x of t equal a control B times u of t. And if you give me this model and you give me the matrices A for the dynamics and B for the control, then I can do, for instance, Kalman, brackets and ranks, and I can tell you whether the system is controllable or not. But here there is no ODE. And maybe some people will say, well, but then maybe the question is not about ODEs. Maybe you should minimize some functional. Okay, I minimize a functional, but with functional I minimize. Nobody is giving me a functional to minimize here. So it doesn't seem to be a problem in optimization or in the calculus of variation either, right? So how do we handle these problems, these classification or supervised learning problems in the context of modern machine learning, but very much using the tools that we have developed previously in the context of traditional control and optimization theory? How do we do it? It's very simple. We say, okay, it's called supervised learning. Why it's called supervised learning is because we always start from a number of scenarios in which we know very clearly what the answer is, right? It's the same as the automatic classifier of photos in your computer, right? Where you say, you take some photos of some of the people and you say, well, this is myself, Enrique, but this is Professor Kai Zhang, or this is my colleague Xu Zhang in Chengdu, who appears with me often in the photo. So then once you teach, you learn the computer that the names of these people are Enrique, Kai, and Xu, then the computer learns, and then whenever scanning the photos, we'll find a photo of someone looking like Enrique, someone looking like Kai, or someone looking like Xu, this photo will go to the corresponding folder. This is supervised learning. So we say, so here I have 1, 2, 3, like 8 items, 4 categories of 8 items. So here I have more or less 32 items. And then I can teach, I can supervise, I can learn, I can teach the computer. I can say, right, build a model. Please build a model so that whenever the item is in this class, it goes to the yellow. The same model should build, right? Should do it in a way that all these green items go to the green and so on. So what are we doing? We have a collection of items. So in this case, 32. So capital N, right, is 32. This is just to the index I is denoting how many items we have in the collection that is completely known, right? The one that allows us to supervise, to build the model. These items live in a Euclidean space of dimensions, say, RD, right? Why D? Well, because these objects can be, I don't know, shapes, or these objects can be, like in here, can be photos, and then the photos are given by pixels, right? So here, the drawings are relatively simple, but still, every drawing lives in an Euclidean space of a dimension D that is relatively high, right? Because here I have included a number of features, so I have shapes that are not very sophisticated, but still I need to distinguish this bottle from this bag, or from this, say, biscuit, or this hamburger, right? So, or these tomatoes, so there are different shapes. There are also different colors that are characteristics to the different items. So typically the banana is yellow, but maybe the tomato is red. So, D is the space of dimensions in which I am embedding my objects so that they are just points in this Euclidean space. Every object is a point in this Euclidean space. So I have 32 objects, capital N is 32, living in a Euclidean space Rd, in which the number of dimensions is large enough so to distinguish the different objects. So by the way, you see here that also you put a glass, you put it on, on the green container, but normally you don't put, glasses on the container. You put glasses when they are broken in the container. This is why there are some cracks on them, right? So this is part of the shape as well, okay? The cracks could be part of the shape. Very good. So we have these 32 objects, n equal 32, in the dimension d of shapes, of objects I have built. Of course, in practical applications, I prefer to keep the dimension d as low as possible, right? Because the higher is the dimension d, the higher the computational cost of everything will be, and the more risk there is that I face the challenge of, the course of dimensionality. And then in supervised learning, you know already many things. So you know that all these items go to yellow. So you can allocate to the index I from 1 to 8, to the first 8 objects, you allocate the label yi, which could be simply yellow. That could be, maybe you are classifying this on the real line, it could be position 0, position 1, position 2, position 3. So with 4 numbers on the real line, I can classify all these items in 4 categories, right? So the labels will be now, YA will be simply, in the Euclidean space R, M equal 1. If I put them on the horizontal line, simply, I just draw an horizontal line, and this is the position 1, 0, 1, 2, 3, right? So then M will be equal to 1. Right? And then what I'm doing in supervised learning, I say, if the ordering has been 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, then I will have the first 8 will go to 0. The second, say, 8 will go to 1, and so on. Of course, if this was disordered in the room, it was, the playing ground of, a park where many kids are playing, so all the toys are randomly mixed, then this will be a little bit more complex, but this is something we can do. And then the question is, the mathematical question is, please build a dynamical system, so that whenever you start from any of the items in this yellow category, the trajectory will land, in the reservoir 0. Whenever you take an initial datum, for instance, here will land in the reservoir 3. Whenever you land, you take an initial datum in the green category, it goes to the reservoir 2, and so on. So, but please make sure that your dynamical system does exactly this job. And then you say, well, but how I am going to find a dynamical system that is going to do something so sophisticated? What are the dynamical systems I know? Well, I can go to the books, and then I know the Navier-Stokes equation, and maybe simplified models in fluid like Barger's equation, or KDV equation, or Sandvenan equation for shallow water, but I don't think it fits. Well, I have the heat equation, I have the wave equation, I can go to finite dimensions and can consider harmonic oscillators, nonlinear penduli, the equations of ballistics, the Nelson car we mentioned the other day, the dynamics of a car on the plane. I have all these dynamical systems. But will any of those dynamical systems that have been developed in order to face specific applications in physics and mechanics, will any of these dynamical systems fit to my goal? Probably not. Then the question is, how to build a model, how to build a model. And model for us is maybe an ordinary differential equation or a partial differential equation that will generate the dynamics of will generate the needed dynamics. Okay, and this is something I will explain you just after our break. So it's now 9:26. So Professor Kai-san, can we meet maybe at 9:35 in 9 minutes? Is that okay?
It's okay, Professor.
Okay, guys, thank you. So we meet at 9:35, okay? So get some rest and drink some water, and we come back here. Okay. Okay. Can we continue, Professor Kai? Okay. So then the question then is, I hope I made it clear. The challenge in the modern applications of machine learning, one of the challenges is how do we build a model for such problems which apparently do not fit within the classical paradigms of mathematical modeling of mechanics. This is not about mathematical biology, where we can adopt the principles of population dynamics and write Log-Cabot-Terra equations for predator-prey. This seems to be different, right? So how do I model this? Okay, and this is where neural networks enter, right? There is a broad literature on this topic. In particular, there is a paper by Sivenko that I would like to, mention briefly here. So this was published in '89, and the name of the paper is Approximation by Superposition of a sigmoidal function. You see here the typical drawing of a neural network, right? We see here two possible sigmoid functions. One is this smooth transition from 0 to 1, which is the hyperbolic tangent. And so this is the one that is called ReLU. This is the rectified linear unit. So this is just the sine plus function, the function that is taking the value 0 to the left for x negative and x to the right for x positive, right? So it's a piecewise linear and continuous function, right? So these are two different sigmoids. So both of them, right, are essentially sigmoids, right? They are different types, but you see that already they share a number of features. So one of the features that they share is that they are monotonic. Both of them are monotonic. Both of them are continuous. This is more smooth than this one, right? And both of them clearly discriminate left and right, right? So here, essentially, of course, there is a transition here, an intermediate phase in which you transit from 0 to 1. But here, clearly, you distinguish left and right. To the left, the function is taking value 0. To the right, the function is taking value 1. While in here, right, you discriminate also left and right, although you do it slightly differently. Here on the left, the value is 0. And here to the right, the value, rather than being nearly a constant, is linear function. Okay, good. So then you see, Sivenko says, approximation by superposition of sigmoidal functions. So what is Sivenko talking about? So what Sivenko is basically telling us is that, you see, you remember from measure theory, right? The classical results saying that every function can be approximated by simple functions. Simple functions are functions that are piecewise constant, right? So what Sivenko is basically telling us is that the same that, I mean, this was also the principle on the Riemann sum, right? The same that you can approximate functions by piecewise linear simple functions, right? You can also do it with functions that are of this sigmoid shape, because basically the only thing you are doing when you are replacing, right, these characteristic functions involved in this piecewise constant jumping function. If you replace the characteristic functions in here by sigmoids, what you are doing is you are replacing these sharp transitions by smoother transitions. Of course, in order to do this, right, in order to make the transitions in here sufficiently sharp, you know you need also to scale the space variable, right? Because if you give me such a sigmoid function sigma x, right? Now when you scale, right? This function sigma, if you scale it when epsilon is very small, right? When epsilon is very small, you will make this transition very, very, very long. So this is why this sigmoid will be now more dispersed. The transition will be long. It will take much longer space to transit from 0 to 1, right? By the contrary, when you take the number lambda, the scaling parameter lambda very, very, very large, then you will be compressing, you know, the transition of sigma, and then you will make this transition very, very, very step. And therefore, you will be adapting much better to the jump of a discontinuous function in here. Okay, good. So this is what Sivenko had in mind. Okay. So then, now, once you see this, you wonder, well, so what Sivenko is basically saying, right? What Sivenko is telling me is that if you take such a function sigma, right? You take a function sigma sigmoid, you could take such a sigmoid function sigma. What Sivenko is telling you is that any function f of x can be approximated by a linear combination of weights times the sigmoid times some scaling coefficients plus some drift parameters, right? This is what Sivenko says more precisely, right? And this is what is called nowadays the universal approximation theorem. Why is called the universal approximation theorem? Is because basically every function, say f, which is continuous, in one or several space variables, because you can, I mean, you just do it in 1D, and then by the same argument, you will be able to do it also in several Euclidean dimensions. Every function, right, f of x, which is nice, continuous, say, can be approximated by such a linear combination. What I'm doing here, what I'm doing in this combination where I am using a number capital N of functions. Of course, N has to be, arbitrary. It's like when you do, when you say by classical Stone-Weierstrass theorem, you say that polynomials are dense. Well, of course, polynomials are dense, provided you allow the degree of the polynomial to be arbitrary, right? So the capital N, the degree of the polynomial, is arbitrary. And this is why you succeed the polynomials being dense. If you tell me polynomials of degree 3 are dense, I tell you no, this is wrong. Because with polynomials of degree 3 in one space variable, you will only have 3 zeros, and therefore you will not be able to approximate a function, a sinusoidal function, which has infinitely many zeros. Right? So if you tell me polynomials are dense, you have to allow me that the degree of the polynomial has to be, arbitrary up to infinity. And this is what we are doing here. If you want to build, the approximation of any function, right? The space of functions L1, L2, the space of continuous functions, any Sobolev space, Besov, whatever the space of functions you consider is an infinite dimensional Hilbert or Banach space. It's infinite dimensional. So you need to allow the dimension to go to infinity. So then, of course, here N is arbitrary, right? N is large, right? And N is allowed to go to infinity. Now we have 3 coefficients. What I'm doing with the B? Well, the B is simply a translation, right? So whenever you add B to the argument, whenever you add b to the argument x of a function sigma, what you are doing is to shift, the center of gravity of this function. And this is natural in this context because you see, I have chosen the sigmoid sigma to be either, this one or this one typically, but this one and that one, they are, their center of gravity is at x equals 0, right? So this occurs at x equals 0 to fix ideas. But of course, when I have to adapt to a function that is, oscillating, I need to place this jumping, this interface at different locations. So I will need different b's. On the other hand, as I have mentioned before, a is a scaling parameter. So when a is epsilon, very small, I make this transition of the sigmoid very long, very mild and very long. By the contrary, when the scaling coefficient a is very large, this transition is very narrow, is very thin and very steep. And I go very fast from, the minimal value 0 to the maximal value 1. And then I need also, of course, this to adapt to the geometry of any arbitrary function that can be mild slope or a strong slope depending on different locations. So it's clear that I need n to be large. I need all possibilities to translate this function. I need all these possibilities to scale the variable x. And then finally, I need the possibility of amplifying also the jump, right, of, the amplitude of the sigmoid by multiplying it by a constant c, which is arbitrary. Why? Because, this sigmoid is jumping from sigma equal to 0 to sigma equal to 1, right? But in practical applications, the amplitude of the jump can be small in some cases and large in the others. Okay, so then you will need the c to adjust to the amplitude of this jump. Okay, so you see that all these ingredients are needed: n large, b, a, and c. So if you try to if you try to approximate any function by this superposition of sigmoid functions, as Sivenko said, you definitely need to allow all these parameters to be free. Okay, this is a necessary condition. What the proof of Sivenko did, and it's very beautiful, I recommend you to have a look to this paper. We can go back during the course if you want to. I can give you now a hint of why the proof, in fact, is quite easy nowadays. It was very innovative at that time. Nowadays, it could be a master exercise. This is an exercise you could do yourself, exercise. Proof the universal approximation theorem. I give you the hint, right? So what I said is that all these ingredients are necessary, but they are also sufficient. And then what Sivenko did was the following. He said, oh, let me see. I have to prove that the class of functions of this form, which can be generated by taking capital N arbitrary, and the coefficients A, B, and C also arbitrary on the real line, I have to show that this class of functions is dense. How do I do it? Well, I apply Hambanach. Right? Hambanach says, assume this class of functions is not dense. Assume it is not dense. We do it by contradiction, right? So we argue by contradiction. And we say, if it is not dense, then there exists a function, say h, let's work in L2, right? Just to simplify things, because then we have the scalar product in L2. We have a function h that is orthogonal to any function that can be written as a superposition of sigmoids a la Sebenko, right? In particular, if h is orthogonal to each of these functions, of course, it means that the integral of h against all these combinations of sigmoids is equal to 0. Of course, h will be in particular orthogonal to every individual, right, sigmoid like this, right? So in particular, because of that, so as a corollary of this, we will have that the integral along the line of h of x sigma of ax plus b dx will be equal to 0 for all a and b. Okay, very good. Now, the next step we do is the following. We say, okay, fix b. So what are we doing when we are fixing the b? We are fixing the center of gravity that will not be 0 necessarily, will be placed wherever I like. And now let a go to infinity. What happens then when a goes to infinity? When a goes to infinity, this transition becomes sharper and sharper and sharper, and eventually the sigmoid becomes the Heaviside function. So when you do this, the sigmoid of ax plus b converges to the Heaviside function, which is 0 to the left of, say, minus b, and 1 to the right of minus b. So you see that what I have proved is that then the function h, in case there will exist such a function, the integral of h, this is not optimal, right? But okay, so now I have the screen clean again. This helps. Right? What I will have out of this argument is that the integral of h will be 0 against each of these Heaviside functions. This means that, you know, the integral of h from minus infinity to b and from b to infinity will always be 0 for every b. Well, why can I do, you know, why can I reverse the sense of the sigmoid so that the integral is not localized only from b to infinity, but also from minus infinity to b? Is because, you know, in this general expression of Sebenko in which I combine sigmoids of this manner on an arbitrary sum, I can also choose the sign of a to be negative. And of course, whenever you take this sigmoid, but then you reverse the sign of a, then the shape of sigma is also switching the trend and now transiting from 1 at minus infinity to 0. So this means that I will have, you know, all these integrals of h to be equal to 0. And then the proof is almost done. The only thing you have to do by Ham-Banach in order to argue by contradiction, showing that this set is dense in L2, is to show that, okay, the only thing I need to show is that each function, so why is it true that any function, say h in, say, L1 of the real line, so that the integral from minus infinity to b of h and the integral from b to infinity of h is 0 for all b, why such a function is necessarily 0? So you know, graphically it means on the real line, the information I give you about the function is that whenever you choose the half line, this one, then the integral here is 0. Now you choose a different half line like this one, and then the integral of h here is 0. Now you take a different half line, this one, and the integral of h is 0 as well. And you take a different half line to the left, and the integral of h is 0 as well here. So how can you show that a function h, so that all these integrals on half line is equal to 0, are equal to 0? How can you show that this function h is equal to 0? Any hint? How can I do it? Well, you can use Lebesgue differentiation lemma, right? What does Lebesgue say? Lebesgue says that in order to evaluate a function at any point, right? If the function is integrable, almost every, any measurable function can be approximated by simple functions. Yes, this is the idea, right? But I mean, trying to make it more analytic, you know, enjoying the fact that I can write on my iPad, I know this is much easier than answering on a chat, right? I can say the following. I can say, well, according to Lebesgue differentiation lemma, the value of f at x0, I know, is the limit as epsilon goes to 0 of the integral from x0 to, right, of the function f dx divided by epsilon, right, or 2 epsilon. So what the Lebesgue differentiation lemma tells you, and this is the starting point of all the variational calculus and the theory of distribution and the modern theory of partial differential equations in particular, because this was like a very, revolutionary switching in the way of thinking about functions, right? So because of Lebesgue, we don't need to think on functions, right, just as objects to be evaluated on points. We can think on functions through momenta, through averages, through integrals. Why? Because even if when you give me averages, integral of functions, you seem to be giving less information. Why? Because in an average, you are mixing many values of the function and you are not isolating individual values of the function. Even if that is the case, out of averages, you can recover pointwise values by a limit process. So this was a great revolution, right? So with this theorem of Lebesgue, then you can build the theory of LP spaces and the suborder spaces and write down equations, in particular partial differential equations in variational forms. And you can apply all the functional analysis to solve partial differential equations. And you can justify the convergence of finite element methods and do many, many other things. So you see, this theorem of Sivenko took a long time. It was only published in 1989. You know, it's, I don't know, it's 40 years later, the book by Curran and Hilbert is published with all, you know, the modern introduction to, say, applied mathematics, numerical mathematics, PDEs, modeling, approximation theory, and so on. So even books like, I don't know, Isaacson Keller on, you know, some of the historical books on numerical analysis, or the books by Jacques Williams on say, functional analysis and partial differential equations out of functional analysis, they were written in the 60s. So the book by Hormander on microlocal analysis was written in the 60s, you know. And if you look to the books, classical books of Lavisenskaya in this Russian school, or I mean, this was much later. Surprisingly, even though the mathematics needed to prove this theorem, this came much later. Why? Well, it was part of the historical development of our society, right? How science and how technology evolved. Until then, people were thinking in the context of mechanics, following Newton, right? We have the law of gravitational forces, and out of this we build the Hamiltonian system for the solar system. Or we have elasticity, right? And we write the wave equations in elasticity to understand, drums, membranes, seismic waves, acoustics. Or we have the Navier-Stokes equations of fluids, and we use them in order to build, the meteorological sciences or aeronautical industry. But here, there was no model. So people have to rethink the foundations of a new discipline, which is this big discipline of data science and machine learning in particular, in which you use the old concepts, but you use them in a completely different manner. Okay? And then, as I said, because this is true, what I'm saying is that in order to show that a function f is equal to 0, in fact, what this theorem of Lebesgue tells me is that the function f will be identically 0 if the integral of the function f is 0 in every subinterval, right? Because if the function f, the average, is 0 in every subinterval, then by the Lebesgue differentiation, the value of the function will also be 0 in the center. But how do I show that the value of f, the integral of f, is 0 in every subinterval? I know it on half lines, to the left and to the right. Well, the observation is quite elementary. It's true. According to this statement here, Hahn-Banach contradiction leads to the vanishing of averages on half intervals, on half lines. How do I get from half lines to the segment? It's very simple. The integral on this segment is just the integral on this half line minus the integral on this other half line. Therefore, because the integrals in each half lines are equal to 0, the integral on every segment is equal to 0. By Lebesgue differentiation, the function is 0 everywhere. And therefore, apply this to the function h coming from Hahn-Banach contradiction, I can guarantee that this combination of sigmoids, superposition of sigmoidal functions a la Sibenko, right, is dense. Okay? So, as I said, this is an exercise for the master course. I recommend you to have a look to the paper. If someone doesn't find the PDF, I can send it to Professor Kaizan. This is, by the way, this was one of the first papers in this journal. I think it was number 2 of this journal that was created precisely back in '89. And nowadays, this is one of the leading journals in mathematical control theory, which is led by our colleague and friend Lars Grune in the University of Bayreuth, close to Erlangen, when I am working in Bayern, in Bavaria, in Germany, right? Okay, so now, okay, fine. This we understood. This could be part of a, an exercise of a master course on the introduction to functional analysis. But this was not the topic of the course, right? The topic of the course was control theory and machine learning. So how do we link this to control theory and machine learning? What is the linking point? Well, the linking point was that I understood that, classical problems like supervised learning, I mean, this is a typical example, but examples could be to many things, right? Of course, including security issues, intelligence issues, supervision of, landscapes, of natural resources, if you are monitoring, from space, whether there is risk of fire in some of the forests in your country and so on, you have to say, oh, risky fire there or not fire, right? So you have to be able to distinguish between just someone, you know, turning on the lights in its garden, right? And the possible risk of a severe fire in a forest that will destroy, you know, a lot of nature, right? And natural wealth. We are always facing problems such as classification and supervised learning. What I told you is that, listen, this is something I can identify with a dynamical system, because it is all about making sure that I have a dynamical system that is able to, you know, to bring the initial point to the destination and simultaneously another initial point to another destination, and then the other one to the other, and the other one to, you know, to the other, and the other one to the other, and doing this with many, many, many points. But what is the model that is doing this? Well, what Sivenko said, listen, you can always do that. Why? Because you see, every function can be approximated by sigmoid functions, right? Therefore, regardless how complex the function you are looking is, right? And this is a function that will, of course, also depend on some time parameter. You could think that there is here some time parameter. So not only you need one Sivenko function, but you need a Sivenko function depending on time, which is able to do whatever you want, right? At every time, you need to reproduce the graph that is required in order to allocate every point X to the corresponding label Y. What Sivenko says, regardless what is the complexity of the function you are looking at, you can build it using simply superposition or combinations of sigmoids. So then it's done. Then what is the common practice then in machine learning? The common practice, I mean, the simplified, the most, say, natural way of proceeding. Then, of course, the devil is in the details, as usual. You will have to learn how to do that, how, depending on whether you do it in one way or another, you know, your algorithms will be faster, will be more efficient, more precise, they will scale better, and so on. The process is this. You say, supervised learning is just about finding functions that are, in particular for us, this will be a dynamical system that is able to bring every initial datum to the corresponding destination, right? Normally, in control theory, you have to do that within a given class. So in classical control, right, you don't have that much freedom, because in classical control theory, if you are looking to how heat diffuses in the building you are working, people will tell you, yes, according to the architecture and the distribution of rooms in the building and the air conditioning system, A is given and B is given. Because A, which is the, you know, mimicking the interconnectivity of the rooms in the building, this is telling you how heat is diffusing, is being transferred from one room to another. There is nothing you can do. The building is done, so A is given. And the air conditioning system, I mean, we made an investment. It's very expensive. It is set already. This is the B. And you have to, you know, the only thing you can do is to regulate that system. So you can choose the intensity of U. You can choose the temperature and the intensity. You have a few, say, actuators to regulate, right? But that's all. You cannot change the B. You cannot change the A. So classical control theory is much more limited by the fact that we are dealing with typically mechanical systems or problems maybe in epidemiology or in population dynamics or in economics or, I mean, wherever the field is, but the dynamics is given. There is a lot of rigidity on it, and therefore the only thing you can do is to, you know, try to do the best possible out of the system you are given, right? This is like when you are a researcher or you are doing, you say, oh, you see, if I had a bigger grant, then I could hire more people and better students and have better collaborators, and then we'll be able to face more challenges. Oh, if I had a bigger computer, I could run bigger simulations, and then my numerical experiments will be, more relevant. Well, yes, that is true, but you have to do with the conditions you are given. This is classical control theory. Now, when we are in the context of machine learning, the dynamics is not given. So I am allowed to build the dynamics. I am free to build the dynamics. Why? Because in principle, plastic, glass, and paper, they don't know about their nature. They don't mind. They don't choose themselves to go to one destination or another. It's not like animal behavior, right? Where, it's not so easy to, to dominate an elephant or a lion, right? They have their own personality, and you better be careful, right? Okay, you could be the victim rather than the guide, right? So here there is not such a problem. There is no personality on all these death items. You are totally free to build a dynamical system that is able to do this. But now the question is, well, can I build dynamical systems that develop dynamics which are completely artificial, like the one of classifying items according to their, to the materials they are constituted of? Is it true that there are dynamical systems doing this? Yes, there are. Why? Because, what Sivenko said, give me any function and you can build such function, something very, very close to it. It's as close that you will not even be able to see the difference, right? Because to the human eye, I don't know whether you ever did the experience of computing, in MATLAB, you take the PD solver and you solve the Laplace equation in 1D, and then you see a parabola. Okay, so the exact solution is the parabola, so it's a very nice quadratic function. You do it with finite difference of finite elements. Of course, you know that the solution given by finite elements is piecewise linear, is not a nice quadratic smooth parabola, it's just piecewise linear. But as soon as you put a number of elements to the human eye, you will not be able to see the gap between the parabola and the piecewise linear approximation. So, because in these problems, in principle, there is not a sharp dynamics that is imposed, but rather just something quite soft, is the necessity of driving points to destinations in an approximate manner. The gap, the error in the approximation, which can be made arbitrarily small by the density argument we developed using Ham-Banach, this error is negligible. And what Sivenko says, everything can be approximated by sigmoids. And this is when a new area for applied mathematics started. People said, oh, then I can do data-driven modeling. You could have a look in internet, you will see plenty of lectures on, and articles on data-driven modeling. What does it mean? It means that, mechanics, that if you are modeling elastic materials, you will use the equations of Lamé, or if you are modeling fluids, you will use the equations of Navier-Stokes. But there are many other scenarios in which this doesn't belong to any of the subfields of mechanics. There is not an a priori modeling paradigm, and therefore what you do is you do it data-driven. What does it mean data-driven? Is that you have data like in here. Here I have 32 items, 32 data. What I'm doing here is data-driven modeling, because I'm modeling a nonlinear dynamical systems. The mathematical tool is the universal approximation theorem of Sivenko, that says that I can build wherever I want out of sigmoid functions just by superposition. This is the mathematical tool. And my source of knowledge is driven by data. It's driven by the fact that I know that these yellow points goes to the yellow, the green to the green, so that, you know, the dynamical system might be very complex. There are different yellow points, but all yellow points will go, you know, they can maybe oscillate a lot, but they have to go all to the same destination, and all the purple points will end on the purple, independent of where they were located in principle, right? They go to the purple, or then, you know, there could be greens, right? But then all go to the green. This is like tourists landing in an airport, right? So there are plenty of tourists getting to Beijing, thousands, millions of them along the year. But every tourist comes with, you know, the reservation, the booking of a hotel. So in a way or another, right, the tourists find their way. And then landing to the airport, each of them will take the corresponding shuttle or bus or metro or taxi, and will go to, you know, the hotel corresponding to their reservation. Okay, this is what we are doing. So this is data-driven, right? This is data-driven. And then, of course, you know, the experience, this is why the hotel or the travel agent will ask you to fill a questionnaire in the end of your stay. They will tell you how happy you were in this hotel. Would you like to come back? Will you recommend this hotel to, you know, to your friends and to your family? Did you find it, you know, good enough? The breakfast was good. It was quiet. It was expensive. Many questions. Why? Because all this is done in a data-driven manner. What the travel agent wants is to learn from your experience, right? Because if they learn that the yellow hotel is bad, they will not put any more tourists in here. They will put them into the others, right? Because in this way, they will increase the satisfactions of their clients. All this is data-driven, okay? And now, as I said, data is, you know, the new mine on which we find, you know, the information, the material, right, to manufacture the new systems. And the new systems are dynamical systems that are able to build, right, nonlinear dynamics, allocating, you know, every item to the corresponding destination. And the fundamental mathematical tool that justifies this is this universal approximation theorem. Now, in practice, you see, having a universal approximation theorem is very useful. Because once I know that every function can be approximated in this manner, I know that the only thing I have to choose is just a number of parameters, right? So if you tell me that, you know, such things are sufficient, then the only thing I have to choose is the A, the B, and the C. And furthermore, I already gave you some hints of how do you choose the A, the B, and the C. The B will be located on the interfaces. The A will be regulated according to the slope of the interfaces. And the C will be just in order to fit the size of the jumps. Of course, the more precise you want to be on your approximation, the more of them you will need, so you will have to increase the N. But you see, in principle, once you know that this theorem is true, the problem just becomes about choosing optimally some parameters so to make the gap on this approximation to be small enough. So it's again an optimization problem. And eventually, you will solve it using the classical tools we knew, like, for instance, IP-opt. Although in principle, IP-opt, this software from Carnegie Mellon, was developed in order to control dynamical systems arising in, chemical industry, chemical engineering. So you see again, this universal nature of the mathematical theory and methodologies, right? Methods that were built in order to solve numerical optimization problems arising in dynamical systems out of chemical engineering turn out to be, the ones you use in order to, just identify the parameters in this universal approximation, which is what you need in order to, build the, the nonlinear dynamics that is able to classify, waste. But you say, well, okay, so all this is very interesting, it's certainly fascinating, but you wonder, but this is a bit stupid after all, right? So in this exercise, I know what the answer is. I know this is plastic should go here. I know glass should go here. I know paper should go here. Do you think anyone will buy? You ask to any friend who is not a mathematician, do you think they will accept that in order to classify waste, they have to study a bachelor in mathematics and then a master in mathematics and maybe even do some training in computer programming and maybe a PhD to solve this classification problem? Anyone could do it. Anyone could do this. So why all this mathematical theory for doing this? Well, because the goal of this machine learning is that machines need to learn, right? And you see again the same principle as Norbert Wiener indicated in the definition of cybernetics, that is the original name for control theory. He said, it's the science of communication and control in animals and machines. Why? Because we humans, animals, intelligent animals, we want to build machines that are able to do our work. Because while the machines are working, we can focus on what we like to do. So you see, I'm talking from Bilbao in Basque Country in the north of Spain to China, maybe 10,000 kilometers away. But the technology, the machines are taking care of everything, of capturing the image, communicating through internet, the signal to, to China, encoding the signal, the image, the audio. So I can just focus on giving them mathematical explanations of my topic, right? So we want the machines to learn. So this is why the name machine learning, right, was Q. And the point is that I'm not doing this very complicated mathematical theory based on universal approximation and control theory and on my understanding of dynamical systems. I'm not doing it just for classifying these 32 items, but the ultimate goal is generalization. So what does it mean, generalization? The generalization means that in supervised learning, you will build a machine that learns how to do the job out of the items, right, you collected, right, and for which you have enough information. Once this dynamical system is built, the goal of this dynamical system is not redoing what you know how to do, of course. This small experiment out of these 32 items, was simply meant to train your neural network, to train, to choose the combination of all these coefficients that will generate, right, the neural network, the combination, the superposition of sigmoids that is able to mimic this complex nonlinear function. once out of this data that you know, that you have, that you dispose of, you are able to train to fit the parameters in your nonlinear function, which is written as a combination of sigmoids. Once you know it, you will use it for generalization. It means that the next time there is a new item coming, right? There is a new item coming, you will not even check. You will not devote your time to discuss whether this coupon here is paper or plastic. You will put it in the machine, and the machine will simply allocate, right, the destination of this coupon out of the nonlinear function that has been given. So once you have this dynamical system, right, that you have trained out of many, many data for which you have given the corresponding, label, and you have built the nonlinear dynamics so to allocate, the correct label to each initial datum, the next time there is a new item, there is this bag, right? So I have this red bag here. Okay, so I think this is a synthetic material. So maybe it should go to yellow, I think, right? If I am getting rid of this bag, I will put it into the yellow. But the next time, I will not think on it anymore. I will just put it in the machine, and the machine will decide, even though the color of this red bag is red, the material is yellow, and it should go to the yellow. So this is why we call it machine learning. The machine could be indeed, a physical machine, but in principle, the machine we, as in our condition of mathematicians, we are thinking of is a virtual machine. The machine is just a nonlinear map, a dynamical system, out of which the Poincaré map from t equals 0 to t equal 1 takes items to be classified and will allocate to them the corresponding, basket. That's it. Okay? So this is how machine learning works. Supervised learning, we use the data known to build the nonlinear dynamics, but the overall goal is not to redo what you know how to do, but to use it for generalization. And generalization means that you are ultimately using this machine, this, say, numerical nonlinear model you have built out of neural networks to classify new items whenever they come, right? And this is something you see already working, right? So for instance, in Germany, in the supermarkets, when you get to the supermarket, there is a machine that is giving you back money when you put, bottles, right? You return the bottles you have bought in the supermarket. You have bought water, milk, soja milk, juice, tea, coffee, whatever, beer. You have bought different bottles and cans and cartons. You have them at home, and then rather than putting it into the garbage, you go to the supermarket and then you put them in the machine. And then the machine gives you a coupon with money out of the number of bottles you are putting. But the machine is intelligent. The machine has learned. The machine has been built based on these principles of machine learning, so that whenever you put a bottle of plastics, it gives you 25 cents, I think. But if you put a bottle of glass, it will give you only 8 cents. Why? Because we are allocating more relevance to recycling plastic than recycling glass. Why? Because, the glass will degrade more naturally and therefore is not so pollutant. So because we want to avoid the pollution generated by plastic, we pay more money to the people that return a plastic can or bottle to the machine in the entrance of the supermarket, right? So then the machine is intelligent. The machine, whenever you put a bottle, determines, plastic or glass, and then according to whether it's plastic or glass, then is yellow or green. But then not only this, actually the output in that case is two-dimensional, right? What the machine does is say, plastic goes to yellow, and then I give 25 cents to Enrique. While glass is green, and then I give 8 cents to Enrique. So you see that, of course, in the space of labels, right, you can have the dimension you like D for the items, if you want to be very, very precise, right? If you are in some biomedical application and you are dealing with, I don't know, brain cancer or some other neuro disease, and you need to, you need to take images out of computer tomography, the images have to be very precise. And then your diagnosis needs that you look to the very details of this image very carefully in order to determine whether, this is a risky situation or not, right? In that case, the data you have will be very rich, and, you will need to be, right, in a Euclidean space of dimension D very large, right? On the other hand, depending on what is the output that you expect, right? Also, the precision on the diagnosis, the dimension M of the output space could vary, right? For instance, so far, we were only discussing a one-dimensional output because we only needed to allocate a reservoir to every item. But in the application I gave you in the supermarkets, you have to allocate a reservoir plus, right, the value of the corresponding coupon. So it's a two-dimensional output. Okay, good. So let's continue then. Oh, let me show you a video. So maybe you have seen it already. It was a bit fast. Okay, let me do it again. So this is a video that our former PhD student, Borjan Geskowski, right? He got a PhD in Autónoma in Madrid in our team this year, 2 months earlier, and now he is working in the artificial intelligence company here in Basque Country in Bilbao, Sherpa Artificial Intelligence, that you can find in internet easily. They do in particular recommendation systems, right? So you know what a recommendation system is. So this is one of the applications, important applications of machine learning is recommendation systems, right? And of course, they are more and more everywhere in internet. So, you can find even recommendation systems on scientific publishers, right? Where they will say, okay, you read often articles in mathematics, and that's your case for sure. Then you are often using the web page of big publishers like Springer, for instance, or Nature, or you are using these web pages in order to search for articles. What these web engines offer you is, okay, you can join our recommendation system, right? So that, right, whenever there will be a new article published in the topics you are interested in, right, then we will send you an alert, right? So in this way, you don't need to be browsing actively every day on internet to see in all these journals how many articles, by whom, what do they say on the topics of your interest. Rather, you can passively wait in your email every, say, week or second week or every month. You will get an alert email telling you, listen, in this week, in the topics of your interest, there have been this and this and these articles published in that and that and that journals with the corresponding reference. This is the author, this is the abstract. Now you have a quick look and you decide whether you want to read more. This is a recommendation system. right? So another example of recommendation system is you are planning your vacation, right? And then you decide, okay, I want to travel to, oh, I want to visit, some of the most, touristic spots in China. Okay, then you choose the cities and they will recommend you the hotels, right? Of course, before that, you will have to give some hints about, how much are you ready to pay per day, right? Because if you don't get the same hotel for 100 yuan or for 10,000 yuan, of course. Okay, good. So recommendation systems on everything, right? And this is what this company, one of the areas of work of this company, and you see here a very successful example of someone getting a PhD in mathematics, and the next week he was already working in one of the most dynamical companies here in Spain on artificial intelligence. So what does this simulation do? So this simulation is a very simple one, but I wanted to show you how efficiently this works, right? You see it in action. So this is the exercise we have. So this is like a soccer game, right? We have recently a lot of soccer games here in Europe because there was the Europe Cup that finally, Italy won, right? Okay, so normally when the soccer game starts, there are 11 players in the blue t-shirt, 11 players in the red t-shirt. So the blue ones are the Italians who won the championship. The red ones are the team in England that finally could not do it. Was just number 2. Okay, so then there are 11 players with a green t-shirt, 11 players with a red t-shirt. They all get into the field before the game starts, a few minutes before, right? But then the referee says, okay, we are going to start, so everyone should go to the corresponding half field. In this exercise, I think the reds have been allocated the left half field and the blues have been allocated the blue half field. But of course, when they got into the stadium, they are all friends, they know each other, they were saying hello, they were running, they were exercising, so they were disordered. So then in principle, then the problem of each person going to the corresponding destination is very much like this nonlinear dynamical system in which everyone has to find its way, probably crossing others that are doing exactly the opposite, right? And avoiding collision. Okay, so how do we do it? Do we have a dynamical system for the motion of the players? Not really. We don't have a, we don't have a system like the solar system based on, on the law of gravitational forces. We don't have a Hamiltonian system to say how every player will walk and run and move within the field. It's hard to anticipate, right? In particular, where each player is will depend on many things. For instance, if one player sees that there is a good friend, watching the match in this corner, maybe he will approach to say hello. So these are, situations that you can hardly anticipate. You need a machine, right? We need an algorithm. We need a nonlinear dynamical system that, independent of what, the initial distribution of blue or reds are, you guarantee that the reds go to the left and the blues go to the right. The same as you guarantee plastic goes to the yellow, basket, paper goes to the blue basket. Can we do that? And then the answer is yes. So you see that this is a dynamical system generated by the principles I mentioned before, based on a neural network modeling, because we don't have an equation from mechanics to govern the motion of the players, right? But we can, based on these principles and using what we know about dynamical systems, control theory, an optimization theory, we can definitely do this, right? And we can guarantee, right, that the dynamical system we build is successful. Okay, so now if you check, is it really successful? Let's see. Let's check with more detail. Oh, I see indeed the blues going to the right. I see the reds going to the left. But do you see any defect on the final output in here? What do you see? So here it seems fine, right? The reds are to the left. And here it seems to be basically okay. So the blues are to the right. But what do you see here? Don't you see a red that is on the blue side? Yeah. So you see it here in the picture in the end, right? So you see the reds on the left and the blues on the right. But there is an error here, right? Why is that? Well, that's because, the principle we have used, which is this principle of the density of the sigmoidal superpositions, the universal approximation theorem, right? There is always some error, right? This is just an approximation. So it's not exactly the function you aimed. Actually, realize that here we are not, in the way density is built a priori is purely theoretical. We say I have a function and I have to approximate it by sigmoidal functions. Yes, that's true. If you have the function, you could approximate it. But in practice, you don't have the function. So you have to guess what the function is out of the approximation. So there is some error built in. And this is why we did that in purpose. Normally, when you will run your machine learning algorithm, the algorithm, if it is well designed, it will work pretty well. But this doesn't mean it will work 100% correct. Actually, no algorithm will be 100% correct, right? Because you could certainly always, wherever the approximation of the function is, except if the functions are really identical, and this is very unlikely because nature is very, very complicated. And even if your algorithm has been trained for years to classify correctly soccer players, right? Even if this has been done for many years in many different countries, in many different leagues, I'm sure there will be new players in new generations that will behave differently and that for some reason they will not be well classified. Because, they simply were distracted. Maybe they are mathematicians playing soccer and then they are not paying attention to the referee, but they are thinking on the challenges on, control and machine learning. And then they were not paying attention to the referee, so they got to the wrong place. So this is typical. You don't need to expect an exact solution. You don't expect a perfect generalization. There will always be some error. And then the question is the error affordable or not? If the error is affordable, okay, you keep it like this. If the error is not affordable, what does it mean? Well, if this error is really not affordable, if this was really for this person in red here, this was a serious risk of having some injury or so, you will say, no, we have to avoid this, right? I mean, you don't cross the avenue. The pedestrian don't cross the avenue with the red light. Too much risk. Okay? You don't do it. So we should avoid this. This is a pedestrian crossing the highway on a red light. No. You cannot do that. So we need to do better. How do you do better? Well, it means that we have to tune our, neural network a little bit better. What do? You will then train the network a bit more. And in order to train the network a bit more, and in order to make a more, say, accurate use of the Sivenko universal approximation theorem, then what I will do is probably increase the n a little bit, add more sigmoids, complexify a little bit the approximation paradigm, adjust better the parameters, and then hope that the next time that you build your neural network, right, not only you will get 99% of accuracy on the classification, but you will get maybe 99.9, and therefore this item will be well classified. But please keep in mind that all this is just approximation theory for an object that we don't know, right? So even in the context of continuum mechanics, I think we mentioned that, I think it was Einstein or so who said that as long as mathematics is exact, it does not really represent the real world. And this is exactly the same here. If someone tells you that they have a perfect classifier for a given process, then you can tell, well, if the classifier is perfect, it's because it's purely mathematical. Because I'm sure in reality, there will always be some exceptional event that will not be well classified by your classifier, right? This is fine. The only thing you need to guarantee when you are working with machine learning in some practical application is that things are done well enough so that the error, you are encountering in your algorithm is admissible for the application. And of course, at this level, different levels of applications, right? Different, say, areas of applications, they allow for larger errors, right? So it's not so important that, the recommendation system of the library of your university from time to time, even if you are interested on control theory and machine learning, they make you the recommendation of an article in algebraic geometry. Well, okay, so it could be also very interesting. Actually, there are many aspects of algebraic geometry also in all these disciplines, right? Because when things get nonlinear and you want to understand, the manifold of solutions, and then there will be what are the crossings of trajectories, then eventually this will lead to problems in algebraic geometry. So why not, right? So in any case, even if this has apparently nothing to do with your topics of interest, it's not so bad. Now, if you are thinking of some medical applications, right, and this machine learning algorithm is used in order to assist the doctor to take critical decisions on whether some person goes to surgery or not, then this is more important, right? And you want this error to be really minimized, right? You don't want to be the patient that gets the wrong diagnosis, like the red one here within the blue, okay? And this is why, of course, then the better, and then the question could be, if you talk to computer scientists, some of them, might tell you, well, but we don't need mathematicians for this, People could tell you, with this result is enough, right? So why don't we stop mathematics at this point? Why don't we say that, sigmoids and the density of sigmoids being true, then it's just a matter of doing, computational mathematics? Well, because the more intelligent you are on how you build these approximations, and there is plenty of, different layers of universe in this approximation theory, the better you build the algorithms in order to, to fit, this kind of superposition of sigmoids, the more complex the problems you are handling will be, right? Okay. That's the idea. This is why also numerical analysis, you could say the same about numerical analysis. Okay, so the initial concepts of finite elements were tuned in the 50s maybe, or in the 60s. It was simultaneous between mathematics and computational engineering. But everyone understood long ago that Galerkin, I mean, that finite elements is just a Galerkin projection of a PDE, and that using elementary, say, density arguments, you can prove the first order convergence of finite elements for classical elliptic PDE. So then, if this was done in the 60s, why people continue still doing this? Well, because there is a lot you can add to this, right? There was, in particular, there was multi-grid algorithms, multi-scale algorithms. Why? Because, you know, nature is not always Laplacian U equal F. Problems can be much more complicated. And because of that, you know, you need to add a lot of layers and years and research efforts, okay? Very good. So this is how the discipline is evolving. You see that, you know, control theory that seemed to be something very classical and very much related to classical applications of engineering nowadays is getting really involved into the topics of machine learning very much. And the interaction is always the same, right? So on one hand, you know, the brain and the machine are cooperating. So certainly the human brain is the most perfect machine, right? We memorize, we compute, we plan, we think. But on the other hand, the machine is a great ally. The machine is not as intelligent as we are, right? So the machines are learning for us, but they are faster than us. They are more powerful than us. They don't get tired. Machines don't need to sleep. They can work day and night. So there is a perfect synergy between humans and machines. And nowadays, this is called machine learning. But this is actually what the goal of cybernetics and control theory is as well. On the other hand, the machine is also inspired not in an individual way, but brain, but also on the whole society and the whole planet. The planet as a network, right? So machines are now cooperating. Okay, so we don't compute only on a single machine. We compute on the cloud, right? So the world of machines is also reproducing, you know, the world of, say, the planet, right? Planet Earth, and the complexity of the oceans and the atmosphere. And then you see how, you know, through the modern paradigms in control theory and machine learning, you know, we are merging somehow these two hemispheres. One is the planet, and the other one is the human brain. So we developed mathematics since many centuries, right? You know, the Pythagoreans were already, you know, in ancient Greece, they were trying to describe everything in the universe through numbers. At that time, the goal was to do it with natural and rational numbers until they discovered that there were irrational numbers as well. Well, they said, fine. I mean, we tried to do it with natural and rational numbers. Now we discovered there are also irrational numbers. So we integrate irrational numbers to the program. And actually, we increase the chances of success, right? Because now with more numbers, more classes of numbers, we can, you know, model more sophisticated paradigms. This was the ancient Greece. Then there was Industrial Revolution not so long ago. Machines and the new mathematics of, you know, industrial processes like control theory. You remember Maxwell being the first one to analyze the stability of the damp oscillator, one of the initial results in control theory, feedback stability of a damp system, of a feedback system. Then we have done the, you know, the revolution of robotics, of cybernetics, of machine learning. We don't know what's going to be next. So maybe you know, maybe you have some guess. You are younger, so you see certainly farther, right? But if you ask me how is going to be the world of applied mathematics, control theory, and machine learning 100 years from now, I don't know. I really don't know what the topics of research will be. Will there be some new fundamental contribution, or it will be more like continue developing the same tool and applying it to more sophisticated, say, innovative technological areas? It will just be that the mathematics are the same, and then maybe just the visualization of the simulations will be done virtually better, and computers will be fantastic, and maybe computers will simply be liquid, and they will be able to represent the dynamics without a solid screen interface. So I don't know, but certainly the future of humanity will be really written, right, in the language of mathematics, right? That's for sure, right? So that you can guarantee, written in the language of math, right? And this is something that Galileo Galilei said already, right? The universe is written in the language of math. It's hard to know, it's hard to see it, right? It's hard to believe and understand it, but it is true. So we don't know how the world will be 100 years from now, but we can really anticipate that there will be a lot of mathematics on the answer to this question mark, right? So the world in 2121, right? 2121, we don't know how it will be, but there will be a lot of math on it. And certainly the math we have mentioned here, everything will be there, and certainly will play a fundamental role on defining the landscape of the new scientific and technological paradigms. Okay, good. So if you want, so the introduction to this course was quite long, right? So we devoted 3 sessions, but I think that was fundamental to do it in this careful manner. So then next class, I think next Friday, we can start now seeing more mathematical content. So this will be like more traditional, because now once we have this general idea, this general landscape of what is the modern theory of control theory and machine learning, we need now to develop contents, right? So we need to learn how to optimize, how to control, how to stabilize, right? How to classify, how to do supervised learning. We will do that in the coming sessions. We have still plenty of time. There are 2 articles that I wanted to recommend you. So there is a paper I wrote with our colleague Enrique Fernandez-Cara, like 20 years back, 18 years back, on the history of control theory. There are plenty of references there. Of course, we are not experts. We are not experts in the history of science, but we did an effort in order to gather a number of interesting events in the history of control theory, and also some interesting bibliography. There are beautiful books on the topic. And I wanted to mention also another paper that was published last year, right? It's a short paper, just 5-6 papers by the Russian mathematician Alexander Fradkov, where he presents the early history of machine learning. And it's really very interesting, because in this paper, you see how, this is why he calls early history of machine learning, how the people that were developing, in this case, he's talking mainly about the Russian school, where you see names like Kantorovich, who won, the Nobel Prize for the transport theory in economics, right? And this is why we call it Monje Kantorovich. People that were doing the traditional applications of control, optimization, with different applications, in particular in the field of economics, in order to plan the development of the former Soviet Union in a more or less optimal manner, according to, to the ideology of the regime and the society at that time. How these people that in principle were mathematicians doing control or optimization theory or combinatorics, right? they were actually building the foundations of what is known today as machine learning, which is just a reservoir where we have put previous knowledge orienting effort to some modern applications. Thank you for your attention.